The aircraft fuel system plays a critical role in safe and efficient flight. Its purpose is simple but vital: to store fuel and deliver the correct amount of clean fuel to the engine at the proper pressure. In this video, we will study aircraft fuel systems step by step, beginning with fundamental concepts and progressing toward practical aircraft applications. The aircraft fuel system is designed to store fuel and supply it to the engine under all operating conditions. It must function reliably during engine start, taxi, takeoff, climb, cruise, descent, and landing. The system must continue to operate despite changes in altitude, aircraft attitude, acceleration, and atmospheric conditions. Every aircraft fuel system must be designed to deliver fuel at the correct pressure and flow rate, so the engine and auxiliary power unit operate properly in all normal and certified flight conditions, including maneuvers. To maintain safe operation, each fuel pump is designed to draw fuel from only one tank at a time, and the system must prevent air from entering the fuel lines. For turbine-powered aircraft, fuel systems must meet strict fuel venting requirements and continue operating even if the fuel contains small amounts of water. The engine must keep running under icing-prone conditions, ensuring reliability throughout the full range of fuel flow and pressure. Each fuel system must be designed and arranged to provide independence between multiple fuel storage and supply systems, so that failure of any one component in one system will not result in loss of fuel storage or supply of another system. To prevent fire hazards, fuel systems include lightning protection. They are built to prevent ignition caused by lightning strikes, electrical discharge, corona effects, or streamering near fuel vents. Pilots must be able to accurately determine the amount of usable fuel on board and receive an uninterrupted supply when the system is operated correctly. The fuel system must also safely isolate or retain fuel during all operating conditions and reduce risks to occupants during survivable emergency landings. The fuel storage system includes the aircraft's fuel tanks and their supporting structure. These tanks are built to withstand flight loads and are isolated from crew and passenger compartments for safety. They are protected against heat and environmental damage, and they store enough fuel to ensure safe operation under all expected conditions. On larger aircraft, the system may also include fuel jettisoning, which allows excess fuel to be safely dumped to reduce landing weight. Fuel refilling or recharging systems allow fuel to be safely added to the aircraft. These systems may use gravity fueling or pressure fueling. They are designed to prevent incorrect fueling, fuel contamination, and hazards to ground personnel and the aircraft. Each aircraft engine is designed to operate on a specific type of fuel, and only the manufacturer-approved fuel may be used. Mixing fuels is not permitted, as it can lead to serious engine damage or failure. Aviation fuels are broadly classified into two main categories. Aviation gasoline, known as AVGAS, is used in reciprocating piston engines and is highly volatile for proper combustion. Jet fuel, also called turbine fuel, is used in turbine engines and has lower volatility with a higher flash point, making it safer for high-temperature operation. Using the correct fuel ensures proper engine performance, reliability, and flight safety. Small single-engine aircraft use different fuel system designs. The layout depends on fuel tank location, such as high-wing or low-wing aircraft, and how fuel is delivered to the engine. Carbureted engines use a different fuel system than fuel-injected engines. The simplest fuel system is the gravity feed system, commonly found on small, high-wing training aircraft. These aircraft typically have two fuel tanks, one in each wing. Fuel flows by gravity from the tanks to the engine, without the need for a fuel pump. The outlets of both tanks are connected to a fuel selector valve, which allows the pilot to select left tank, right tank, both tanks, or fuel off. When the both position is used, fuel from both tanks feeds the engine simultaneously. Because both tanks can feed the engine at the same time, the space above the fuel in both tanks must be interconnected and vented to the outside atmosphere. The vent line usually exits on the underside of the wing, where fuel siphoning is unlikely. After leaving the selector valve, fuel flows through the main fuel strainer, which removes dirt and water. From the strainer, fuel flows directly to the carburetor inlet. Fuel for the engine primer system is also taken from the main strainer. Low-wing aircraft cannot rely on gravity to supply fuel to the engine, so fuel pumps are used to provide the required pressure. These systems typically include an engine-driven fuel pump and an electric fuel pump for backup. The fuel selector valve usually allows selection of the left tank, right tank, or fuel off, but it does not include a both position. This prevents the pump from drawing air if one tank runs empty. After passing through the selector valve, fuel flows through the main strainer and then to the electric fuel pump. The electric pump and engine-driven pump are installed in parallel, allowing either pump to supply fuel independently. Before engine start, the electric pump is switched on to check fuel pressure. After start, it is turned off to confirm the engine-driven pump is operating. The electric pump is used during engine start as a backup in case the engine-driven pump fails and to maintain fuel flow while changing tanks. In high-wing aircraft equipped with a fuel injection system, such as the Teledyne Continental system, a portion of the fuel is continuously returned to the fuel tanks. This returned fuel carries fuel vapors with it, helping to prevent vapor lock and ensuring smooth engine operation. Fuel flows by gravity from the wing tanks through front and rear feed lines into small accumulator or reservoir tanks. From the bottom of these reservoirs, fuel is directed to the fuel selector valve. The selector valve not only routes fuel to the engine but also directs separated fuel vapors back into the vent space of the selected reservoir tank. An electric auxiliary fuel pump then pushes the fuel through the strainer and supplies it to the engine-driven fuel pump. From there, fuel flows to the fuel control unit, which precisely meters the amount required by the engine. Any excess fuel is returned to the pump inlet, while vapor-laden fuel is routed back to the tanks, maintaining proper pressure and preventing fuel vapor formation in the system. Many small multi-engine aircraft are equipped with the RSA fuel injection system. Unlike the Teledyne Continental system, this design does not return excess fuel to the tanks. Each wing contains two interconnected fuel tanks that function as a single fuel source. Fuel selector valves allow either engine to draw fuel from either wing tank, a feature known as crossfeed. From the selector valve, fuel passes through a fuel filter, then an electric fuel pump, followed by an engine-driven pump, before entering the fuel injection system and finally being delivered to the engine cylinders. The system is monitored using fuel quantity gauges, fuel pressure gauges, and fuel flow indicators. Fuel flow is measured by a differential pressure gauge and displayed in gallons per hour or pounds per hour. Large multi-engine aircraft powered by reciprocating radial engines, such as the DC-3, are no longer produced, but many are still in service. These aircraft typically use carbureted engines and fuel systems similar to those found in smaller aircraft. In the DC-3, each engine has a selector valve that allows fuel to be drawn from either a main or auxiliary tank. Fuel flows through a strainer to an engine-driven pump and then to the carburetor. A crossfeed system allows one engine to supply fuel to the other if required. Early aircraft used a hand-operated wobble pump for priming, while later models replaced it with electric pumps. Fuel pressure is monitored through gauges and warning lights to alert the crew of any loss in pressure. Jet transport aircraft use fuel systems designed to safely and efficiently deliver large quantities of fuel. In aircraft such as the Boeing 727, fuel is stored in multiple tanks, including integral wing tanks and fuselage-mounted bladder tanks. The wing tanks are built into the wing structure itself, while fuselage tanks use flexible fuel cells. Electric boost pumps in each tank supply fuel to the engines, and a crossfeed system allows any tank to supply any engine when selected, providing operational flexibility and redundancy. Fueling is accomplished through a single-point pressure fueling system, which automatically shuts off to prevent overfilling. The same system allows controlled defueling when required. During flight, fuel may be jettisoned to reduce landing weight. Fuel dump systems release fuel safely from the wing tips, while maintaining engine supply and proper balance. Dump limit valves ensure fuel dumping stops before engine operation is affected. We've covered jet transport aircraft fuel systems in greater detail in an earlier video, which you can access using the link displayed above. Helicopter fuel systems vary in complexity depending on the aircraft type. Most helicopters use one or two fuel tanks located close to the aircraft's center of gravity, usually near the main rotor mast in the aft fuselage. Some tanks are positioned above the engine for gravity feed, while others rely on pumps and pressure feed systems. In basic systems, fuel flows from a vented tank through a strainer, shutoff valve, and main filter before reaching the carburetor. Light turbine helicopters typically use in-tank electric boost pumps that send fuel through shutoff valves, airframe, and engine filters, and then to the engine-driven fuel pump. These systems include vented tanks, electrically operated sump drains, fuel pressure gauges, and warning switches for filter restrictions. Fuel quantity is measured using in-tank fuel probes. Larger multi-engine transport helicopters use more advanced fuel systems, similar to those found in jet transport aircraft, with multiple tanks, cross-feed capability, and pressure refueling systems. In conclusion, aircraft fuel systems vary widely depending on aircraft size, configuration, and engine type. However, all fuel systems share the same goal: to deliver clean fuel at the correct pressure, reliably and safely, under all operating conditions. Understanding fuel systems is essential for safe aircraft operation and maintenance. Thank you for watching.